In modern naval warfare, range is not the same thing as reach. A missile that can travel 200 nautical miles is irrelevant if the system cannot generate a firing quality track at the required moment. That distinction defines the geometry now shaping the Eastern Mediterranean. In February 2026, two U.S. supercarriers operate on opposite sides of the Middle Eastern battlespace. In the Arabian Sea, the USS Abraham Lincoln positions near the maritime choke points tied to the Persian Gulf. Its air wing, including F-35C squadrons, backed by Super Hornets, forms a self-contained strike complex. Closer geography reduces sensor friction. The flight deck can project power with shorter chains of coordination. But further west, the USS Gerald R. Ford anchors in the Mediterranean under a different constraint. The decision to remain outside the effective range of Iranian ballistic missile systems is rational. Distance increases survivability, yet distance also increases latency, degrades sensor geometry, and introduces line-of-sight limitations. This is not a tactical mistake. It is a structural trade-off. Iran's integrated air defense network, anchored by long-range systems such as the Bavar-373 and S-300PMU2, projects radar coverage across layered airspace. Combined with the elevation and mass of the Zagros Mountains, this creates a natural extension of the radar wall. Surface-based naval radars, even advanced phased array systems, operate within the laws of physics. They cannot bend electromagnetic energy over the curvature of the Earth. They cannot see through terrain. The Ford carries interceptor missiles capable of striking threats hundreds of miles away. Its vertical launch cells are deep. Its combat systems are mature. But magazine depth does not replace sensor access. A ship can only engage what it can track, and track quality degrades rapidly when terrain masking and curvature intervene. This is the central paradox. The fleet holds long-range kinetic power, but the battle space is geometrically obscured. Positioning further offshore reduces vulnerability to ballistic attack. However, it increases dependence on external sensors. The carrier strike group transitions from being a largely organic strike entity to becoming a node within a broader ISR and command architecture. The moment it does so, interoperability and data latency become decisive variables. The question is not whether the Ford is powerful. The question is how that power is routed. How do you launch a long-range interceptor when your primary radar horizon ends before the threat begins? How do you strike targets behind mountainous terrain without exposing the fleet to the very anti-access network you are attempting to dismantle? These are not rhetorical questions. They define the operational calculus of contested maritime environments. The United States Navy must extend its sensor horizon without collapsing its survivability margin. It must create an elevated, survivable sensing layer that can function inside hostile electromagnetic conditions. The constraint is not political, it is geometric. The carrier's standoff distance preserves the hull, but it fractures the kill chain. Until that fracture is repaired, the fleet holds firepower without access. To repair that gap, the system must change shape. Two carriers in theater do not represent redundancy. They represent two different geometries of risk. In the Arabian Sea, USS Abraham Lincoln operates closer to the maritime approaches connected to the Persian Gulf. The battle space there is constrained by shipping lanes and choke points. Airspace is dense, but sensor lines are shorter. Organic carrier aviation can cycle sorties with tighter timing loops. The distance between detection and engagement is compressed. That compression reduces dependency on external nodes. The Eastern Mediterranean is structurally different. USS Gerald R. Ford sits west of the Levantine coast, deliberately outside the projected reach of Iranian ballistic missile systems. This positioning is not symbolic. It is defensive geometry. Anti-ship ballistic missiles increase probability of kill as range closes. By remaining further offshore, the carrier reduces exposure to saturation attack and preserves maneuver options. However, every nautical mile added for survivability subtracts clarity from the sensor picture. Surface-based radars operate on line-of-sight principles. Even advanced phased array systems cannot see beyond the curvature of the Earth. When mountainous terrain such as the Zagros Range intervenes, radar shadow zones expand. The result is a fragmented battlespace picture. This is where the anti-access architecture becomes relevant. Long-range surface-to-air missile systems like Bavar-373 and S-300PMU2 are not isolated launchers. They are integrated nodes within a network of early warning radars, fire control systems, and distributed command elements. Their purpose is not simply to shoot aircraft down. Their purpose is to deny approach corridors and force adversaries into predictable paths. For the Ford Strike Group, the issue is not magazine capacity. Vertical launch cells provide depth. Interceptors, such as long-range surface-to-air missiles, can engage targets at extended distances. But these interceptors require high-quality track data. Without a stable track file, a missile becomes an expensive ballistic guess. The carrier's air wing provides flexibility, but it is optimized for maritime strike and fleet defense within manageable radii. To dismantle a dense inland air defense network across mountainous terrain requires sustained penetration and survivable sensing inside contested airspace. That is a different problem set. Institutionally, this is where naval architecture intersects with joint force design.
It is not designed to
The Navy's capital ships are built to survive and project power at sea. They are not designed to independently collapse a land-based integrated air defense system deep inland without support. That limitation is not a failure of engineering. It reflects design prioritization. If the carrier remains outside the ballistic envelope, it must extend its sensing layer forward. If it moves closer to solve the sensing issue, it increases missile vulnerability. The system must choose which risk to carry and how to distribute it. The Ford, positioned in the Mediterranean, therefore becomes dependent on a solution that can operate inside the anti-access zone while remaining survivable enough to maintain track continuity. Without that forward node, the carrier group retains firepower but lacks penetration. This is the point where joint integration ceases to be optional. It becomes structural. The limitation facing the Ford Strike Group is not a shortage of weapons. It is the absence of a survivable forward sensor operating inside the radar wall. An integrated air defense system such as the one built around Bavar-373 and S-300PMU2 functions through layered detection. Early warning radars establish broad search coverage. Fire control radars refine tracks. Data is fused and distributed through hardened command networks. When paired with terrain elevation like the Zagros Mountains, the defensive system gains natural masking advantages. Aircraft flying low are shielded by terrain. Ships operating at sea are constrained by horizon limits. Surface combatants equipped with advanced phased array radars can track ballistic and aerodynamic threats within their line of sight. However, curvature and terrain create blind zones that cannot be solved by increasing radar power alone. The equation is geometric. Increasing transmitter strength does not remove physical obstruction. Interceptor missiles launched from vertical cells require continuous or mid-course updates to achieve high probability of kill at extended ranges. Without a persistent track, engagement envelopes shrink in practice. A 200 nautical mile missile does not guarantee a 200 nautical mile engagement if targeting data collapses before intercept. The strike group therefore confronts a classic systems dilemma. It possesses deep kinetic inventory, but lacks persistent interior sensing within the denied zone. Carrier-based aircraft can provide reconnaissance, but survivability inside dense, long-range surface-to-air coverage becomes uncertain without prior suppression. This is where force design assumptions matter. The Ford-class carrier was not built around the expectation of unilateral penetration of a mature inland anti-access network. Its value lies in generating sustained sorties, managing distributed operations, and anchoring maritime control. The task of opening a corridor inside a hardened air defense network often falls to specialized stealth platforms designed for air dominance and deep penetration. The Navy's Carrier Air Wing includes fifth-generation aircraft, but in this scenario, the density of inland coverage and the distance from sea-based support complicate sustained operations. The fleet requires an aircraft optimized not only for low observability, but also for high-altitude supercruise, long-range air superiority, and survivable sensor fusion deep inside contested airspace. The structural solution is therefore joint. Instead of repositioning the carrier closer and accepting ballistic risk, the system can project a forward sensor and shooter from land bases closer to the theater. This preserves the carrier's survivability margin while extending the kill chain inward. However, projecting such a platform across the Atlantic is not instantaneous. Air dominance fighters optimized for combat maneuvering are not optimized for intercontinental transit. Moving them into position introduces a new set of constraints rooted in fuel capacity, tanker availability, and mechanical reliability. The problem shifts from geometry over the Mediterranean to physics over the Atlantic. Deploying a high-end air dominance platform from North America to the Middle East is not a symbolic movement. It is a logistical event governed by fuel fractions, drag coefficients, and tanker availability. The F-22 was engineered for air superiority inside contested airspace. Its design priorities include low observability, supercruise capability, and high thrust-to-weight performance for sustained high-G maneuvering. Internal weapons bays preserve stealth geometry but reduce internal fuel volume compared to aircraft designed for long ferry missions. In combat configuration, range is acceptable. In intercontinental transit, it becomes restrictive. To cross the Atlantic, the aircraft must attach external drop tanks. This immediately alters the radar cross-section and increases parasitic drag. The continuous curves that minimize radar return are disrupted. Aerodynamic efficiency degrades. Fuel consumption rates increase. The aircraft transitions from optimized stealth interceptor to fuel-dependent transit platform. This is the reality of a Coronet mission. In U.S. Air Force doctrine, a Coronet deployment is a tightly coordinated, tanker-supported, long-distance fighter movement. It is not a simple transfer. It requires a synchronized aerial refueling bridge, weather windows, maintenance reliability, and contingency planning for mechanical anomalies. Tanker availability becomes a limiting factor. Modern tankers such as the KC-46 introduce digital systems and new refueling architectures, but they also carry developmental and integration risk. Electrical or systems anomalies during launch sequences are not theoretical inconveniences, they halt missions. When support aircraft experience faults, the entire formation must abort. In this environment, gravity and fuel margins do not forgive rounding errors. Initial scrubbed launches from the U.S. East Coast illustrate institutional discipline rather than weakness. High-value assets are not pushed through uncertain conditions. Protocol demands reset, inspection, and recalculation. Each abort consumes time. Time, in a developing crisis, is a strategic variable. Once the tanker bridge stabilizes, the fighters stage through the United Kingdom. Maintenance crews operate in cold weather conditions, preparing airframes for the next leg toward the Middle East. Fatigue accumulates across pilots and ground crews. Fuel logistics scale upward. Every additional nautical mile requires planning layers invisible to the public narrative of rapid deployment. Even then, attrition can occur before combat. A single fuel leak in a drop tank, a pressure anomaly, or a mechanical irregularity forces separation and return. Aircraft may divert. Numbers fluctuate. The deployed force becomes a function not only of intent, but of mechanical reliability. By the time the fighters arrive in theater, millions of pounds of fuel have been consumed. Dozens of support aircraft have participated. Maintenance cycles have compressed. The operational spearhead exists because the logistical base absorbed friction. The geography problem is addressed. The aircraft are now positioned closer to the denied airspace. But proximity alone does not integrate them into the naval fight. A stealth aircraft that cannot securely exchange data with the fleet is an isolated node. It may see targets, it may survive inside hostile airspace, but without a secure translation layer, its sensing advantage cannot be converted into naval firepower. The constraint shifts from fuel and thrust to the electromagnetic spectrum. Arrival in theater does not equal integration. The F-22 operates using a proprietary intra-flight data link, or IFDL. This link is designed for low probability of intercept and low probability of detection. It transmits narrow, directional beams between Raptors, minimizing electromagnetic exposure. Within an F-22 formation, sensor data, track files, and targeting information are fused and shared with high survivability. The aircraft remain electronically disciplined. The carrier strike group in the Mediterranean operates on a different communications architecture. Naval forces rely on Link 16, cooperative engagement capability, and related NATO standard tactical data networks. These systems are robust, widely interoperable, and designed for distributed maritime operations. They are not optimized for extreme emission control inside dense electronic warfare environments. Here, the structural paradox emerges. The most survivable air superiority platform in theater cannot natively speak to the fleet without compromising its stealth profile. If an F-22 transmits broadly on Link 16, it generates omnidirectional radio frequency energy. That emission can be detected by hostile electronic support measures. In a contested environment, persistent emissions create trackable signatures. Low observability is not only about shaping and materials, it is about electromagnetic discipline. A single unnecessary broadcast can negate hours of careful approach geometry. Therefore, maintaining stealth requires restricting how and when the aircraft communicates. From a systems perspective, this creates a fracture in the kill chain. The F-22 can detect, classify, and track targets deep inside the denied zone. The carrier strike group possesses deep magazines and integrated air and missile defense. But without a secure translation layer between IFDL and naval networks, sensing and shooting remain decoupled. The solution is architectural rather than platform-centric. Instead of forcing the F-22 to alter its emission profile, an intermediary node can absorb the translation burden. A high-altitude relay platform operating above most surface-based threats can intercept the Raptor's directional transmissions, decode them, and reformat the data for naval networks. In this scenario, a U-2S operating in the stratosphere carries an open architecture processing pod capable of ingesting IFDL data streams. At approximately 70,000 feet, the aircraft sits above much of the threat envelope of traditional surface-to-air systems. Its radar cross-section is large relative to stealth aircraft, but altitude provides a degree of survivability through geometry and standoff. The onboard processing system functions as a data translator. It receives narrow beam transmissions from the F-22, decrypts and reformats the track data, and forwards the information through tactical targeting network terminals and Link 16 down to naval units. In effect, the U-2 becomes a bridge node linking incompatible architectures. This introduces a deliberate trade-off. The system accepts the vulnerability of a non-stealth relay aircraft in order to preserve the stealth of the penetrating fighters. It centralizes a portion of the kill chain in a single high-value node. If that relay is disrupted, degraded, or destroyed, the integration collapses. However, without such a bridge, the fleet's long-range interceptors remain constrained by horizon limits. The risk of concentrating functionality in a relay aircraft is weighed against the operational necessity of connecting sensors to shooters. The network is now technically connected. The geometry gap is reduced. The fighters can see. The fleet can receive. The next question is whether this architecture can function under active electronic attack. With the relay architecture in place, the network can pass data. That does not mean the airspace is permissive. Before any kinetic strike package moves inland, the integrated air defense system must be mapped with precision. Modern suppression does not begin with bombs. It begins with passive collection. Land-based F-35s operating under emission control can use their electronic support measures to detect and classify radar emissions without transmitting. They collect frequency, pulse repetition, scan patterns, and triangulate emitter locations in real time. This is not dramatic. It is mathematical. Each radar site reveals itself by radiating. By measuring slight differences in angle and timing, the aircraft construct a geolocation solution. That solution is packaged and transmitted through secure channels back to the broader network. The objective is to identify the eyes of the defense system before attempting to blind them. Once emitter coordinates are validated, electronic attack assets move forward. EA-18G Growlers, launched from the carrier, accelerate toward the threat envelope. Unlike stealth aircraft, they are not optimized for invisibility. Their role is deliberate emission. Equipped with next-generation jammer pods, they project targeted electromagnetic energy into specific frequency bands used by hostile radars. The intent is saturation, not subtlety. By injecting high-power noise and deceptive signals into radar receivers, they degrade track stability and overwhelm processing capacity. False targets appear. Real targets fragment. Command networks experience latency and confusion. An integrated system begins to lose coherence. This phase carries risk. Electronic attack aircraft must operate within range of the very systems they are attempting to disrupt. Timing is critical. Jamming must align precisely with penetration windows. If synchronization fails, stealth assets may enter airspace before radar degradation is sufficient, increasing exposure.
Each layer depends on the previous
When
one.
the jamming effect peaks and radar tracking is degraded, the F-22 formation advances. Supercruise at high altitude reduces infrared signature and preserves energy. Rather than diving into dense terrain where maneuvering would bleed speed and altitude, the aircraft exploit gaps created in radar coverage. Terrain masking from mountain ranges further complicates residual detection. This is coordinated sequencing: passive detection, active jamming, stealth penetration. Each layer depends on the previous one. Remove one element and the structure weakens. At the same time, the relay aircraft in the stratosphere continues translating track data between fighters and fleet units. The carrier strike group receives updated air picture information beyond its organic radar horizon. The kill chain is no longer theoretical, it is live. However, contested airspace is dynamic. Once primary radar nodes are degraded, adversaries adapt. Mobile launchers may reposition. Low-altitude threats, such as cruise missiles and unmanned systems, can exploit clutter and curvature to approach maritime targets. When such low observable or terrain-hugging threats emerge, the value of elevated sensing becomes clear. An F-22 operating at 50,000 feet with advanced radar modes can detect anomalies that surface radars cannot see due to horizon limits. Instead of descending and engaging directly, the aircraft can offload track data through the relay to naval combat systems. A destroyer operating under the Aegis Baseline 9 architecture can process off-board targeting data and launch interceptors such as the SM-6 using remote queuing. In this configuration, the ship does not require organic radar contact at launch. It relies on networked track continuity. The missile climbs, receives mid-course updates, and engages based on shared sensor data. This is integrated fire control in practice.
Every added layer of integration
Sensor and shooter are geographically separated, but digitally unified. The curvature of the Earth no longer fully protects low-altitude threats if elevated sensors provide persistent tracking. Yet the system remains fragile. It depends on data integrity, timing precision, and the survivability of relay nodes. Electronic warfare can target data links. Cyber intrusion can attempt disruption. The more complex the network, the more pathways exist for interference. The airspace may be temporarily opened. The fleet may extend its reach inland, but every added layer of integration increases both capability and vulnerability. The question is no longer whether the Navy can project power. It is how resilient that projection remains when the adversary shifts from radar denial to alternative sensing methods. When ground-based radar coverage degrades under sustained jamming, the defensive system does not disappear. It reconfigures. An integrated air defense network deprived of stable radar tracks can shift emphasis toward infrared search and track systems and airborne interceptors. Legacy aircraft equipped with infrared sensors do not rely on ground radar in the same way. They attempt to exploit thermal signatures and visual acquisition, particularly if they can draw stealth aircraft into lower altitudes where background clutter is reduced. This shift attempts to change the engagement geometry. If stealth aircraft descend into thicker air and engage in close-range maneuvering, their advantages in radar cross-section and beyond visual range engagement shrink. High G engagements increase fuel burn, energy bleeds rapidly. Sustained dogfighting becomes a contest of endurance and numbers, rather than geometry and timing. The F-22's design philosophy discourages that transition. High altitude and speed are not symbolic. They are energy reserves. At approximately 50,000 feet, air density decreases significantly. Parasitic drag drops. Supercruise at Mach 1.5 without afterburner preserves both infrared discipline and kinetic advantage. Remaining high allows the aircraft to maintain both potential and kinetic energy. Within this envelope, the aircraft operate as a distributed sensor grid. Through directional low probability of intercept links, formations share track files internally. Each aircraft contributes to a fused picture. Rather than descending to visually identify targets, they rely on sensor fusion and long-range engagement solutions. When hostile fighters attempt interception, they often carry external fuel tanks to extend patrol duration. Those tanks increase radar reflectivity and infrared signature. From altitude, the F-22's radar and passive sensors detect these signatures earlier than the opposing aircraft can detect the Raptor. Engagement occurs beyond visual range. The F-22 does not illuminate continuously with active radar. Instead, it can provide mid-course guidance updates to launched missiles through secure data links. Only in the terminal phase does the missile's own active seeker activate. By that stage, reaction time is minimal. This approach is not theatrical. It reflects energy management and emission control discipline. The aircraft avoids unnecessary maneuvering. It avoids prolonged exposure. It leverages altitude, speed, and networked targeting to conclude engagements before close combat develops. As the hostile interceptor presence diminishes, the airspace corridor widens. The stealth air dominance platform does not remain to conduct sustained strike operations. Its role in this architecture is to clear and stabilize the approach path. Once suppression and air superiority conditions are established, other assets assume the strike burden. Heavier platforms, whether long-range stealth bombers or carrier-based strike fighters configured with larger ordnance loads, move through the corridor created. Their survivability improves because the initial layers of detection and interception have been disrupted. From a systems perspective, this is layered task allocation. The F-22 provides forward sensing and air dominance. Electronic attack platforms suppress emitters. The carrier strike group supplies magazine depth and sustained sortie generation. Each element operates within its design envelope. However, the architecture remains dependent on synchronization. If tanker support is disrupted, endurance drops. If the high-altitude relay is neutralized, data fusion fractures. If jamming fails to align with penetration timing, exposure increases. The corridor may be open temporarily. The network may function under stress. But the durability of this construct depends on maintaining cohesion across air, sea, and electromagnetic domains simultaneously. The system has demonstrated that it can extend naval reach beyond horizon limits. Whether it can sustain that reach under prolonged attrition is a separate calculation. Once the air corridor is established, the architecture shifts from penetration to exploitation. With primary radar nodes degraded and interceptor aircraft neutralized, the environment transitions from denial to conditional access. This is the moment when heavier strike assets enter the battle space. Stealth bombers carrying deep penetration ordnance and carrier-based strike fighters configured with larger payloads can now operate with reduced exposure to long-range surface-to-air engagement. The F-22's role does not expand into mass strike. It contracts back into overwatch. High-altitude presence maintains deterrence against residual airborne threats while minimizing fuel expenditure and preserving airframe life. The aircraft remain inside their optimal energy envelope, avoiding unnecessary descent or extended loiter at inefficient altitudes. Meanwhile, the carrier strike group capitalizes on the corridor. With off-board targeting data integrated through the network, surface combatants can extend air and missile defense beyond organic radar horizons. Interceptors, such as long-range surface-to-air missiles, can be cued by remote sensors. Magazine depth at sea becomes a strategic reserve rather than a constrained defensive tool. This configuration illustrates a broader principle of modern naval warfare. Power projection is no longer defined solely by the number of aircraft on a flight deck or missiles in vertical launch cells. It is defined by the ability to connect dispersed sensors and shooters into a synchronized architecture. However, each layer added to this architecture introduces stress points. The tanker bridge that enabled transatlantic deployment remains essential for sustained air dominance sorties. Fuel consumption at supercruise altitudes is lower than afterburning flight, but still significant. Sortie generation rates depend on maintenance cycles, spare parts availability, and refueling capacity. The high-altitude relay aircraft remains a critical node. Although positioned above much of the threat envelope, it is not invulnerable. Long-range surface-to-air systems, if reconstituted or repositioned, may attempt to challenge high-altitude assets. Electronic warfare aimed at degrading data links can disrupt the translation layer that binds the network. At sea, the carrier's survivability margin depends on continued standoff from ballistic missile arcs. If the strike group moves closer to shorten sensor chains, ballistic exposure increases. If it remains distant, it must rely on off-board sensing to sustain inland reach. The trade-off persists even after initial success. Operational tempo also becomes a variable. Sustained high-intensity operations place strain on aircrew, maintenance personnel, and logistics chains. Precision munitions inventories deplete. Replacement timelines depend on industrial production capacity and transportation pipelines extending back to the continental United States. From an institutional perspective, this operation demonstrates integration across generations of platforms. Legacy high-altitude reconnaissance aircraft, fifth-generation air dominance fighters, electronic attack platforms, and surface combatants equipped with advanced combat systems. The effectiveness of the system emerges not from any single platform, but from disciplined coordination. Yet coordination is fragile. Disruption in one domain propagates through the network. If adversaries adapt by targeting tanker aircraft, relay nodes, or satellite links, the architecture must reconfigure or contract. The carrier strike group has extended its reach inland without repositioning closer to the threat. The geometric limitation imposed by curvature and terrain has been partially offset through airborne sensing and networked fire control. But the system remains in motion. In contested environments, equilibrium is temporary. Each adaptation invites counter-adaptation. The next phase is not about whether the corridor can be opened. It is about whether it can be held under sustained opposition and shifting threat profiles.